Today we're on page 11 of the student note packet in the purple page section. We're talking about the graphs of the exponential and logarithmic functions. Now on your test, I'm going to ask you guys to hand graph a log and exponential function. And so we're going to use the transformations that we learned last year in AS Algebra 2 in order to apply the transformations onto an exponential or logarithmic function graph and then plot some points. So this top side, or the first page, of page 11 of the student note packet, is just going to be kind of looking at the difference between log and exponential graphs. And then we'll actually get to the back page, page 12, which is going to look closer to something you guys will see on the test. So let's start with number 1, and then I'm going to kind of jump around, and you guys are going to pause and kind of catch up and check your work as we go through the front, and then we'll do the back together. So number 1, we're asked to write the coordinates of the points plotted on each graph and then write the equation of the asymptote. So in this case, we've got the graph f of x is equal to 3 to the power of x, which means that this is an exponential function. There's no log here. And I just want to identify the ordered pairs, and then we'll talk about the asymptote and kind of the shape of what an exponential function looks like. So if we're looking at 3 to the power of x, I'll start right in the middle. This is 0, 1. If I plug in 0 for x, we're going to get 1. And then this is 1, 3. This is going to be 2, 9. This is 3, 27. This is 4, 81. And then going backwards, right, this is negative 1, and then that's 1 over 3. That's 3 to the power of negative 1, or 1 over 3. Negative 2 is going to be 1 over 9. It's 1 over 3 squared. Negative 3 is going to be 1 over 27. And then negative 4 is going to be 1 over 3 to the 4th power, 1 over 81. All right, so we've got all these ordered pairs. Now we also know that there is an asymptote here. We are never going to cross the x-axis. That's because we can never take the number 3 and raise it to any power to get 0 or any negative number. So our asymptote then is the line y is equal to 0. And so if we're looking at the domain and the range, the domain here is all real numbers. I can plug in any number for x, but the range is going to be all the values of y that are strictly greater than 0. So we'll take a look at that. That's really important, especially when we get into solving log equations and things like that. I think that looking at the domain and range graphically can kind of help remind us how to solve equations of logs algebraically. So we're going to skip over to number 5, and there's a reason I'm doing these out of order. So if you guys take a look at number 5, we have this. The function is equal to the log base 3 of x. So I'm going to do this. When we graph logs, I really don't like graphing them in this form. So what I'm going to do is I'm going to rewrite this. Instead of f of x, I'm going to rewrite it with a y. And then I'm going to put this in exponential form because I can actually make a table of values when we've got exponential form, but without a calculator, I don't really know how to calculate things in log base 3. So exponential form tells us that 3 to the power of y is equal to x. So I am plotting all of the points that relate x and y in this way. Now, I did this out of order specifically because number 5 is the inverse of number 1, which we just did. We just swapped x and y. So logs and exponential functions are inverses of one another, which is really nice. That's how we can use logs to solve for exponents and exponents to solve for log equations. It's because they're inverses of one another. They help us out with that. So in this case, if I'm going to plot the points here and identify them, all I'm going to do is I'm going to take a look at the points from number 1, and I'm just going to flip the x and the y values. So instead of the point 0, 1, this is the point 1, 0. And then instead of the point 1, 3, this is the point 3, 1. This is going to be the point 9, 2. This is the point 27, 3. And then we've got 81, 4 all the way out here. I'm just taking the ordered pairs from its inverse in number 1 and flipping the x and y values. So then down here at negative 1, we're going to have, instead of negative 1, 1/3, it's going to be 1/3, negative 1. And then we're going to have 1/9, negative 2, 1/27, negative 3. Okay, so we're just switching the x and y values because logs are inverses of exponential functions. So it makes it really easy if we look at it in exponential form, I think, over logarithmic form. Now, there's also an asymptote when we have logs. This time, though, it's a vertical asymptote. The asymptote here is the line x is equal to 0. So exponential functions have horizontal asymptotes. Logarithmic functions are going to have vertical asymptotes. And if we take a look at the domain and the range, we are restricted in domain this time. I cannot plug in any number for x that is less than or equal to 0. We don't have anything on the left-hand side of the y-axis. And that's because this time I cannot plug in any number for y and get a negative value or a 0 for x. So our domain here is x must be greater than 0. So that's why we have restrictions when we're taking the log of a number, when we go back and check our solutions, when we're solving equations algebraically. This is why we can't take the log of a negative number or 0. It has to be strictly greater than 0. And then the range, though, is all real numbers. So y can be anything. We can plug anything in for y here because y is the exponent if we look at it in exponential form. All right, so now is a good time to pause the video, go back and do 2, 3, 4, 6, 7, and 8, and then come back and check your work. I'm just going to put those solutions up really quickly, and then we'll move on to the back. Number 2 looks like that. Asymptote is y is equal to 0. Answer to number 3, again, it's an exponential function, so the asymptote is y is equal to 0. Last of the exponentials, I would like to note here that I rewrote this. Instead of looking at it as a fraction, I'm going to look at it as an integer base with a negative exponent this time. And then when we are getting into the hand graphing of things, it's going to be a little bit easier for us to identify any transformation. So this indeed would be a transformation. A flip over the y-axis is happening here. So we see that the direction of this graph is different than the first three. These are the points that we get. The asymptote is still y is equal to 0. Our domain is still all real numbers. Our range is still all the values of y that are greater than 0. But we've just got to flip over the y-axis. Number 6 is the inverse of number 2. Again, I'm going to rewrite this log in exponential form. And it's going to be a lot easier when we get to actually graphing logarithmic functions if we look at it in exponential form instead. So we're just going to switch the ordered pairs from number 2. The x and the y values are going to swap, and then we have the asymptote at x is equal to 0 this time. Number 7 is not the inverse of any of the exponential functions we graphed above. So I'm going to rewrite it in exponential form. We get 6 to the power of y is equal to x. And then all I'm going to do to evaluate the x values, I'm just going to plug in the value of y first to get those ordered pairs. So at the top, right, y here is 3. So I just plug in 3, take 6, raise it to the power of 3. We get x, which is 216. So that's how I'm finding those ordered pairs there. The asymptote is x is equal to 0 if we're looking at the domain and the range. The domain is all the values of x that are strictly greater than 0. And the range is all real numbers. Last logarithmic function, number 8, I am going to take the logarithmic form, rewrite in exponential form. In exponential form, we still have that fractional base, which I don't care for, so I'm going to rewrite 1 over 7 as 7 to the power of negative 1. And so when I apply the power of y also, we get 7 to the negative y is equal to x. So that's our logarithmic function in exponential form. We note that anytime we take y and we make it negative, that's a flip over the x-axis. So we see a logarithmic graph being flipped over the x-axis as the transformation there. And then the ordered pairs look as such. The asymptote is x is equal to 0. And again, our domain and range, the domain are all the values of x that are strictly greater than 0. And the range is all values of y, all real numbers. Okay, so let's actually apply this to a graph by hand. So the first thing we're going to want to do, we're going to do everything in steps. And you can do each step over itself. So you don't have to do 4 separate graphs. You can just do like one graph with all the transformations on it in your homework. But we're going to start with standard form. We're going to start with a parent function, and then we're going to apply all of the transformations. Now remember that we go in order of stretches, flips, and shifts. If we follow that order, then we will get the correct graph at the very end, but the order matters here. So we'll start by graphing the parent function. In this case, it's just 7 to the power of x. Our base here is 7. It's whatever number is being raised to the power of x. And so our standard function is 7 to the power of x. So I am going to sketch a graph that is 7 to the power of x. And then what I'll do is I'll transform those points based on the equation that we're given. So I'm going to plot as many points as I can here. When x is 0, y is 1. When x is 1, y is 7. 1, 2, 3, 4, 5, 6, 7. I'm not going to be able to fit 49 on there, but I will graph like this point here, which is 1 over 7. And I know that the general shape of my exponential function is going to look like this. It gets steeper as we go, and it's going to approach the x-axis but never cross it. So that's where I'm going to get really picky about grading these graphs. It's making sure that we graph the asymptote correctly and then we never cross it. Okay, so stretches, flips, and then shifts is the order we're going in here. So let's identify any stretches. Now stretches come from taking our parent function and multiplying it by a value. So if we're looking at stretches here, there would be a number in front of that 7. It'd be like 2 times 7 to the power of x. In this case, we don't have anything other than that negative sign, and that negative sign is going to be a flip. So we actually don't have any stretches here. So we can move on to the flips. Now, we have one flip. It's the negative on the outside. So based on our transformations from last year in AS Algebra 2, this is a flip over the x-axis. We're taking all the y values and we're making them negative. So if you have positive y values, you're making them negative. You're flipping all those points over the x-axis. So what I'm going to do is I'm going to take my graph from step A, and I'm just going to flip all of those points over the y-axis. So that point 0, 1, instead of 0, 1, it's 0, negative 1. Instead of 1, 7, it's 1, negative 7. Instead of negative 1, 1 7th, it's negative 1, negative 1 7th. And so we see our graph flip over the x-axis. Still don't cross it. There's still an asymptote there. We make sure that we graph that, but there's our flips. And then the last thing are those shifts. So there are actually 2 shifts in order to get us to our final equation. X plus 3 and then plus 2. So if we think back, that plus 3 there, that's a movement left 3. And then the plus 2 is up 2. So I'm going to take every single one of those points from step C, and I'm going to move them left 3 and up 2. So let's do that. Got to bring my x-axis down a little bit. All right. 0, negative 1 is going to go left 3, up 2. We're at the point negative 3, 1. And then I'm going to transform negative 1, negative 1 7th. It's going to be right about there. And then the point 1, negative 7, left 3, up 2, we're at negative 2, negative 5. Now, that asymptote is also going to shift up 2. It also technically shifts left 3, but because it goes on forever and ever and ever, we don't actually perceive that. So we also want to make sure we graph that asymptote, and we want to make sure that our graph now is never going to cross that line. So the domain and range shifts a little bit here because we've got those shifts. That's our final graph. Part D. So like I said, you guys can do each one of these transformations on the same grid if you want. Do it in like a different color or whatever, but just make sure you guys are showing the transformations. So that is an example of an exponential function. I'm going to do an example of a logarithmic function and then give you guys time to try 2 on your own. So number 10 looks like this. We've got 2 log base 4 of negative x minus 3. So let's talk about the parent function first. The parent function is inherently like essentially what we've got. So we have a log base 4 of x situation with a bunch of other things, transformations. So we're going to start with the parent function, which is just log base 4 of x. But I don't actually think that this is helpful when we are graphing this by hand in this form. So what I'm going to do is I'm going to switch this over to exponential form. And exponential form tells us this: 4 to the power of y is equal to x. And so all I have to do is make a t-table of values, and I'll just plug in these points to plot my points for the parent function. But what we're going to do here with exponential functions, the trick is we're just going to pick values of y to plug in. So I'm going to go with -1, 0, and 1 for y, and then see what we get for x. So when I plug in -1 for y, we're going to get 1 over 4. When I plug in 0 for y, we're going to get 1. And when I plug in 1 for y, we will get 4 for x. So those are our 3 ordered pairs that we're going to graph here. And I'm just doing that using exponential form instead of logarithmic form. Okay, so let's plot these points, see what we get, and then we'll transform as we go. So 1/4 -1 is down here. I'm not scaling today just so we can kind of see what's going on. You are definitely welcome to scale. 1, 0, and then 4, 1. Okay, so this is a logarithmic function, which means that we're going to have an asymptote now sitting along the y-axis, and our function will get bigger and bigger for all values of x, like that. All right, so that's our parent function. So once we've gotten there, we can actually just ignore everything to do with that log and just apply the transformations as we see them from Algebra 2. So stretches, and then flips, and then shifts, and we'll do them in this order. So there is a stretch here. We have a stretch of 2. So we're taking all of the y values of our original parent function, and we are multiplying those values by 2. So go back to the t-table down here. Take all those y values and multiply them by 2. When I do that, these are the points we're plotting now. I've made a new t-table where I took all the y values of the parent function, I multiplied them by 2, and these are the points we're going to plot on the graph. So 1/4 -2 now. We've got 1, 0, that doesn't change, and then we've got the point 4, 2. We still have that asymptote sitting on the y-axis. The stretch doesn't change that, and I'm just going to graph that function. Okay, so we've got our stretches. Now we do have one flip. So the flip, if I'm writing the equation here, would look like this. It's that -x on the inside. So in this case, when we've got an x on the inside being multiplied by -1, this is a flip over the y-axis. If we think about it, we're taking all the values of x and we're making them negative. So if I take positive values of x, I make them negative. We're flipping those points over the y-axis. So that's what we're going to do here is we're going to take all the points from step B, and we're just going to flip them over the y-axis. So now I'm plotting the point 1/4, -1/4, -2, excuse me, -1, 0, and then -4, 2. Because we're flipping over the y-axis, our asymptote still stays the same. And we're looking like that now. Okay, last part is then the shifts. We have one shift to get to the final equation. And that shift is on the outside. That is a shift down 3. So we're taking all of those points from C and we're going to shift everything down 3. So I'm going to bring up the x-axis so I can see all those points a little bit better. And then down 3, I'm going to take all those points. So I'll start in the middle. -1, 0 goes -3, -1, -3. All right, -1/4, -2 is going to go -1/4, -5. And then 4, 2 is going to go, -4, 2 is going to go -4, -1. Because we had a shift down, that does not impact the way that our vertical asymptote looks. Our vertical asymptote is still sitting on the y-axis, and our final graph looks like that. So the only difference between graphing logarithmic and exponential functions is where y and x are. So always change a logarithmic function into exponential form, make the t-table there, and then just start the transformations off of that. So go ahead and pause the video and give 11 and 12 a try, and then I will put the answers to 11 and 12 up so you guys can check your work. All right, step by step for number 11, the parent function is y is equal to 3 to the power of x. Our base here is 3. That's the number being raised to the power of x. This is an exponential function, which means it's going to have the asymptote along the x-axis, and I just plugged in points for x to find y. We get negative 1, 1/3, 0, 1, 1/3, and 2, 9. There are no stretches because there's no number on the outside. Again, a stretch would look like this: 2 times 3 to the power of x, or 4 times 3 to the power of x. Those are what stretches would look like in an exponential function. So we don't have any of those, so we can skip that step. Step C then, we've got 2 flips. This time we've got a flip over the x and a flip over the y. So when I do that, we get the graph. The asymptote stays the same, still sitting on the x-axis. And then finally, our step D, this is the trickiest one, so please make sure you guys got the correct transformations. This is a transformation right 1 and up 4. So anytime we're identifying transformations and we have to deal with flips, we always want to make sure that the coefficient of x is positive 1 in order to identify the correct movement left or right. So I had to factor a negative out of the exponents up top to get that we moved right 1 instead of left 1. So just make sure you guys did that correctly. You moved everything to the right 1 and then up 4. And then also our asymptote must shift with the movement up. So we've got that vertical shift up, which means we push our asymptote out 4 as well. And we just want to make sure we graph that asymptote and then don't cross it. I'm going to walk through this example. Again, I think it's just good to have another example of graphing a log function. So if you tried it and you want to fast forward to the end to check your work, then go for it. But I'm going to start by looking at the parent function here. This is log base 2 of x. So the fundamental log here is log base 2 of x. Now, again, we're graphing these by hand, so that's not helpful. I'm going to rewrite this in exponential form. And when I do, I get 2 to the power of y is equal to x. And then I can make a t-table of values. And this time I'm going to plug in numbers for y in order to get x. So when y is negative 1, x is 1/2. When y is 0, x is 1. And when y is 1, x is 2. And those are just good starting points to graph this log. So I'm going to plot these points here. And then we'll go from here. I'm going to plot a couple of more too. When y is negative 2, x is 1/4. And then when y is negative 1, x is 1/2. And then we've got 1, 0. We've got 2, 1. And then I can keep going. If I plugged in 2 for y, we would get 4 for x. And then I can actually go one more. When y is 3, x is 8. So this is the curve of my logarithmic function. And the more points I have, the easier it is to kind of see this example work out. So logs, the parent function logs with no transformations, always have that asymptote sitting on the y-axis. So we've got that vertical asymptote there. And then we move on to stretches. So this time we do have a stretch. It's that number sitting in the front of our log here. We're not doing flips yet, so I'm just going to do positive 1/2. And so all I'm going to do is I'm going to take those ordered pairs from my first table, and I'm just going to multiply the y values by 1/2. That's all I'm doing. So the x values don't change. The y values get multiplied by 1/2. So I get negative 1/2, 0, and then 1/2. So I'm just dividing essentially all the y values of that parent function by 2. So let's do that and see what happens. Okay, so I am going to get negative 1/4, negative 1 this time. And then we're going to get 1/2, negative 1/2. Looks like that. And then 1, 0, still doesn't change. And then 2, 1/2. And then if I'm looking at The next point, which we had, was 4, 2. That's now going to be 4, 1. And then that last point, 8, 3, is now going to become 8, 1.5. So I just shrunk this. I shrunk all the y values here from our parent function. Asymptote stays the same. That's our stretch. Okay, we do have a shift here, or a flip, excuse me. That comes on the outside, so this is a flip over the x-axis. All right, so we're going to take all of these points and we're going to flip them over that x-axis. Okay, so we're taking the points from part B. We're going to flip them over the x-axis. So that first point, which is 1/4 -1, is going to go 1/4 +1. And then the point 1/2 -1/2 is going to go 1/2 +1/2. 1, 0 stays the same. And then we've got 2 1/2 is going to go 2 -1/2. And then we have 4 1 is going to go 4 -1. And then that last point is going to be 8 -1.5. Still have the asymptote there. We just flipped all those points over the x-axis. Okay, very last step then are those transformations to get the final curve. We've got the +5 on the inside with the argument and the -3. So the last step here is to shift left 5 and down 3. So we're going to take all the points from part C, go left 5 and down 3. Our final curve looks like that, and you've just graphed your second log. So with logs, just always make sure to convert into exponential form first. If you need to, make the t-table. If you don't need to make the t-table, you can do it in your head. That's fine as well. And then shoot me emails if you guys have questions.